Okay, so. Line through the intersection of two planes. Okay, well, you have to. Okay, I'm not gonna use numbers because they're limited and, you know. Pretty obviously have the aptitude to understand it this way. Okay. If I got a class of people that are struggling, sometimes we'll have to start with numbers, and we don't get as much done. And nobody's struggling because, well, hopefully nobody will. Okay, so what do we do to find the line of intersection? These two lines, two planes. I would like to stop the recording. Okay, so. You need a vector and a point. Now, what vector? The vector in the direction of the line, and I'm not going to write in the direction of the line because it takes time. Okay, I assume everybody understands that. Okay, so. There will, right? The vector parallel to the line. To be N1 cross N2. Right? Or N1 and N2 are normal over plane to N1. And N2. And you should know why those are normal, because you should understand a plane as a set of points such that the vector from some fixed point to any point on the plane is normal to this other vector. You write down what that means, and you immediately get an equation. It can be rearranged to this form, or these are the normal vectors. Well, each plane has this normal vector. Okay. So. Okay, now point on the plane. I don't really need to go to all the trouble of eliminating Z between these two. Because unless one of the normal vectors is parallel to a coordinate plane, you're going to have all possible Z values on that line. Okay. So unless the line is parallel to the XY, one of the lines is parallel to the XY plane, you're going to have a slope in the Z direction. Essentially, your normal vector won't be vertical, it'll be like this. So your plane is going to be perpendicular to that normal vector. So every possible Z is going to be represented. Okay. So you can kind of check that out and then just plug in any number you want for Z, like 0. Okay. So that works. Now, more generally, you could solve this for Z and then plug whatever you get in for Z. Now you have an equation in X and Y. Okay, but let's just assume the simple case. So you get this, right? Well, what the heck, we let Y equal 0. Again, unless something is perpendicular to the wrong thing. But if it doesn't work, we try something. Okay. Oh, wait a minute. There should be a point where X and Y are both 0. It's not necessarily going to give you equal values of X. Yeah, the plane isn't going to go through. Okay. You get what I said. They just solve the system of simultaneous equations for X and Y. Okay. So what I was about to say was kind of dumb. Make sure you say that as comments. Okay, so we solve for X and Y. Get a point which we'll call X naught, Y naught, 0. So this is a degenerate system, solve the point. Those are in linear algebra. We've gotten into simultaneous equations yet? Okay, you will. Give you a better perspective on this. But it's easy enough to do. Solve by elimination or substitution if you like. But elimination is going to work better with your linear algebra because that's what you're using linear algebra. You don't do any substitution because everything's linear and you don't need it. And then you get matrices you can reduce and all that stuff. Okay. So substitution unnecessary and counterproductive in most of linear algebra. Okay. But you should know it. It makes it part of the calculus. That's part of algebra 2. Even algebra 1 for 2 equations and 2 unknowns. So you should know it. Okay, anyway, you solve it, you get a point. Now you got the equation of the line, right? Okay, now, so you got the line. Parameterized by t times b. For v is this vector. Plus your x naught, y naught, z naught, point on the line. Okay. So let's just say that this point is down here in the xy plane. I'm not going to draw x, y, and z axes. Because we don't need them. That's pretty big point. This point is x naught, y naught, z. We could have picked any value at all for z. And unless one of the planes is flat, parallel to the XY plane, we get a result. Okay. And if it is flat, then it's even easier to get according to the point on that plane. Okay. So anyhow, here we have it. Might as well draw the vector B. Okay. Now here is our given point. Oh, that's 1, y1, 2, 1. Okay. this vector would be this. Okay. Now, I think the question was the distance from this point to this line. The distance from this point to this line, we don't know what the orientation of this is, so I'm going to say that right here is a line from x1, y1, z1, your given point, to the given line, right? It's at a perpendicular, so that the length of this line is the distance of this point to the line, isn't it? Well, made a bigger picture so I have room to label it. But let's try. This vector here is the projection of V on U. Projection of what's W? W is this vector. So here's W. So we project W on V. And then this vector here is well, this vector plus this vector equals W. Okay. So we positive vector here. And this vector is then and I'm going to get it written correctly. Yeah, it's a projection of W onto V, not the projection of V onto W. Okay. Picking up my notation as I went and wrote that down wrong. Okay. So again, we project W onto V. That's V dot W, right? Divided by the magnitude of V times the magnitude of W times W over the magnitude of W. In other words, this leg of the triangle times a unit vector in the direction of V, and that's it, the W question. V. You can go back to the way I developed that. You really want to understand that. You don't have to memorize that formula and use it mindlessly, because if you do, you don't see this. And if you didn't really nail that whole idea of projection and the formula for projection and how it tells you the picture of projection, you're less likely to see this, which is why I told you what I told you the way I did. Okay, so take a lesson. There's usually a good reason, and I tell you, you want to know this. It's the foundation, something you use again and again, and it helps you develop pictures that allow you to solve moderately challenging problems such as this one. Okay, I get a lot more challenging than this, and they will before the end of the day. But still, at this stage, when you haven't seen this before, it's a pretty challenging problem. Okay, it should become less challenging as you visualize and see more and more. You get more and more experience. Okay, the other one was the equation of a sphere. Answer to a given plane, center to a given point. Okay. again. Okay, well, we got the given point. We got the plane. Here's a sphere. Here's X1, Y1, Z1. Here's your plane. Not necessarily vertical, but it's easier for me to draw a tangent to something vertical, so I drew it that way. Okay. Now. X naught, Y naught, Z naught is any point on the plane. Over here, I assumed that Z was 0, so the point I got was X naught, Y naught, Z naught. But I can pick any Z. Again, as long as the normal of the plane is not vertical. Not the Z direction, not multi-objective. Okay. Then I'm going to use the same construction I used there, which is why another good reason to understand the projection deeply. It's really important stuff. Very foundational stuff. Okay, so I've got this vector Z. I've got the normal to the plane. What's that? A1I plus B1J plus Z1K, right? I'll just write that. Well, I don't have any. There's a normal vector. What's my distance from here to the plane? Project this vector onto a normal vector. Okay. Yeah, think through the geometry of that, make sure you visualize it. Because it's not trivial. Some of the harder stuff you can do with equations of lines and planes, okay? It's not simple. But it's not excruciatingly difficult. It's modern. You can do it. You can visualize it. You can get better and better at visualizing. Do a lot of sketching. A lot of schematics. Okay. Now, the reason for this, of course, is that any radial vector, okay, is going to be perpendicular to the plane of the sphere. The one that meets the plane here, though, is okay. And it's the vector where the line from the origin to the point of intersection, the single point of intersection between the plane and the sphere, is perpendicular to both the plane and the sphere. It's got to be radial, perpendicular to the plane, got to be parallel to the normal vector. Okay. So now that's two. I think there might have been a third thing I wanted to talk about. Those are the two big ones. Glad they came back into my feeble memory. I got up too early this morning, so lucky I remember which class this is. This is Calculus 3, right? Okay, you look like my Calculus 3 class, I suspect that that's correct. Okay, get off. Okay. So now, got this function parameterized by x of t, y of t, z of t. Okay. So that gives you some kind of a path. Let t run from A to B. So I've got some point here on the plane. This is defined by the vector v from t equals a. So there's a vector in order to out to here. So here's my initial point. This is the t equals a point. I would say an example. Saying how we get circles and ellipses, all that stuff. You review parameterization and all that stuff. So this should be fairly straightforward, at least until we start doing crazy stuff. But it doesn't get that crazy, but when you get the oscillating stuff, it's a little bit challenging. Okay. Again, challenging kind of like this is, but you use a lot of the same pictures. Okay, so we've got the t equals a point. Now we've got some code. We've got the t equals b point. Now we often actually, like I say, don't expect the right terminology. Going to be taken with the right information. Not right or wrong, there's nothing wrong with B. But typically we're going to use R of C. Okay. Instead of B, I call this R of C. And this is the vector R of A. But not at some point in the plane up. We've got we've got three dimensions. You don't know how deep this is going or how far it's coming out of the axis, just what. But there's some curve down here. The vector R of B. This is the typical B point. Okay. Let's say that this is vector R of T. And this is the vector R of T plus delta T. Well, then, we're going to say that the derivative of this, the rate of change of R is change in R divided by change in T. Okay, so thing you can't read is average rate equals, okay? Should be able to read that, average rate, I just couldn't write very clearly, it's unwisely left myself, okay? That makes sense? Now, where's delta R in this picture? Can you make me just a quick sketch? You don't have to sketch the whole picture. Just sketch an R and an R plus delta R and show me, sorry, an R of T and an R of T plus delta T. Just sketch me two vectors. I have the directions of those. You don't even have to put axes on it. Just slap down two vectors. Call one R of T, call the other R of T plus delta T, and show me where delta R is. Okay, well, not everybody got this. Well, delta R equals this minus this. Then how could you write this as an addition? You could write R of T plus delta R equals R of T plus delta T. So it comes down to the question of what vector would you add to R of T? First vector you write down the label T, whatever, wherever you label it. What vector would you add to this to get this? I mean, how do you do vector addition? It's head to tail, right? Which ought to be second nature. If it isn't, make sure it gets there because you're going to need it. And it's not difficult. Okay, you just keep using it because you're going to use it again and again and again. Okay, I think I said it. I don't know if I have the recorder on, but you can write this as an addition. Just add R of T to both sides. Algebra trivial. R of T plus delta R is R of T plus delta T, right? I mean, if this is so, then this follows instantly. So delta R is what you have to add to R of T in order to get R of T plus delta T, right? Now I just drew two vectors here. Said, what's the direction of the vector I'd have to add to this one to get this one? And everybody pointed this way. That's right. Right here is the vector. And you can see, you understand head to tail addition, which I certainly hope you do. But if you add this to this, you get this. Okay. Now, what's the direction? What you have to add to this to get this point again? Yeah. I emphasize this because this is critically important. You can't understand the derivative unless you understand this picture. Okay. Or to put it positively, in order to understand the derivative, we start by understanding this picture. Okay. So I wanted to make sure everybody understood the picture. You understood how to connect that with a fairly simple, straightforward line of reasoning, which you ought to remember. Okay. This makes it easier to think through things. All right. So, actually, that was on a board. As far as I feel safe moving. Okay. So. Average rate of change of R with respect to T is delta R over delta T, which is R of T plus delta T minus R of T over delta T. Now that should look like something that's extraordinarily familiar to you if you understood anything about first semester calculus, other than how to follow some rules to take derivatives and Yeah, maybe some applications, that's significant. I'd say you got that. Did you get this? Okay, well, that summarized my writing. That was a good answer. The guy, somebody said the derivative. Yeah, well, yeah, that was an excellent answer. I'd love to see that. Even better, I would like to hear difference quotient, the limit of which as delta t approaches zero is the derivative, but you know, or at least remember. Okay. And I commented that in my pre-calculus class, are gonna die for me trying to get them to understand the difference quotient, because in my opinion, it's criminal to teach pre-calculus and have students come out not knowing the difference quotient because it's pre-calculus. One of the first things they see in the foundation, the whole first semester. Okay. And you know, I try to do it. It's a tough sell. When people come out of their prerequisite courses not knowing how to solve linear equations. Okay. They will need to be able to solve linear equations. There's one of the prime things you want to be able to use to understand asymptotes and all kinds of other things. Okay. Understand what the derivative is doing before you get the derivative. So, didn't like that in, you left them while you didn't, because I'm sure you saw it. It's one of those things you can get through pre-calculus with without really understanding it, because you can answer the test. Try to get out of that mode, because it's going to be much more beneficial to do. Not saying there's anything wrong with you for having done that, and the course lets you get away with it. Try to push a little harder. I know you have time to that's directly related to what I've been saying about these pictures. And all that stuff and the uses you make of it. These are fundamental things, just like difference quotients. Not quite as fundamental as difference quotients, but it's pretty fundamental to a lot of things. Okay. Okay, so, well, I might that's a lot. Makes sense? Can you kind of read that the same way? Just zero. Now, what is R of t? X of ti plus y of tj plus z of tk. So write out this limit. In detail with the definition of R of t in terms of X and Y. Okay, so I said, okay, here's R of t. I was going to ask you what's R of t plus delta t, but then I decided what's R of R bar. Well, R of t is this. If you say R of R bar, now t is replaced by the R bendable bar. Right? Okay. So this is X of R bar. I plus Y of R bar. J plus Z of R bar. Okay. If X of t is t squared, then what do you get here? What's X of R bar? If X of t is t squared, then f of R bar has to be R bar squared. I don't like to pick on R bar. It's the first word in the dictionary. When I was very first learning to play the piano in the first week, there was a song, Arnold the R bar. I didn't particularly like it, but it stuck with me. Okay. So I don't know if it goes back to Arnold, the arbitrary or, so what is R of T plus delta T? Well, I'm going to continue to try to pull it out. I mean, it's X of T plus delta T. I plus Y of T plus delta T J plus V of T plus delta T K. All right. Okay. Now, that's exactly what it means. That's exactly what function notation means. Okay. So make sure you really understand what function notation tells you. Okay. So I can write this now. Well, you get what times R plus what times J plus what times K all over delta T. What? Yeah, you got two I components, two J components, two K components. Simple algebra, you put them together. It's an obvious simplification. That makes sense? So write down that obvious simplification. If it's not obvious to you, it's okay. Just make sure it becomes obvious by the time we're done. Okay? Or by the time you're done processing it, which will be after class at some point. We don't know what the function x is. So there's nothing we can do to simplify x of t plus delta t. It is just x of t plus delta t. If x is a squaring function, then it'd be t plus delta t quantity squared, t squared plus 2t delta t plus delta t quantity squared. Okay? If it's the exponential function, it would be e to the t plus delta t, which is going to behave algebraically very differently than the square does. Now, if it's a linear function, then, and some of you are trying to treat things like they're linear functions, function notation, you can't do that. Oh, you know what I did here? I did something pretty terrible. I didn't put this difference. I did put parentheses rounded R of T, okay? So you're making mistakes, well, just watching it. Okay. Now, what we then do is we can write this as x of t plus delta t minus x of t I. Here's I, here's an I. Here's a j and here's a j. This is y of t plus delta t. And they're both multiples of j, so we can factor the j out and bring it down. Okay. And then we have this. Now, taking a lot of time, but I don't want to skip anything. Limited delta t goes to zero. I'm kind of writing an unnecessary intermediate step, but I'm afraid it's necessary. Okay, I want you to see every step and then put it all together so you understand what's going on. Okay. Limited delta t goes to zero of quantity. Oh, we got up too early this morning. Okay. Okay, so we have, I'll write it this way. X of t plus delta t minus x of t over delta t times I. Because of course, just dividing by delta t, it distributes over the addition here. Or the multiplication by reciprocal delta t distributes over addition because we don't really state a distributive law with addition. But it's never, since there is multiplication by reciprocal. We don't state it because it causes people to do terrible things with their expressions. Okay. Anyhow, y of t plus delta t minus y of t over delta t j plus z of t plus delta t minus z of t over delta t. Okay. At which point she said, aha. Well, I can say that this is a limit. As delta t goes to zero of x of t plus delta t minus x of t over delta t times I, factoring out the I out of the limit altogether, because you can always factor the constant out of the limit. Plus the limit as delta t goes to zero of y of t plus delta t minus y of t over delta t times j, plus it should be obvious that you're going to do the same thing with z and k, right? So it should be obvious that you write this down too, but I don't have room. What's this? Well, limited delta t goes zero. This is by definition the derivative. Okay. Or df dt evaluate at t. So And this is dRdt equals this limit, because that's the definition of a derivative. It's the limit of the change in R over the change in T as delta T goes, as the change of T goes to zero. If we interpret T as time, this, if X, Y, and Z are positions and T is time. So when you take the derivatives of the X, Y, and Z, multiplying by I, J, and K, you get a velocity. Now, if you come back to the original picture, cover the original picture where it's going on to. And if you haven't seen stuff like this, you haven't done stuff like this, you really need to. Because you don't understand now at this point why these are velocities or why the derivatives of these are accelerations. You just say, okay, it's a velocity to acceleration, go on, and you lack an image of analogous to not really having the image of a projection and not being able to use that to find the equation of a circle tangent to a given plane centered at a given point. Okay. Which, as I said, is a moderately challenging problem. Have a couple of days to learn enough to do that, and some people have trouble with it. Okay. And didn't have trouble with much else in the assignment. You're doing fine, but we want you to make the A you're capable of making, so you need to get these things, if possible. Okay, so now we got this thing moving along this path, wherever it is, 3 dimensions. It goes in here, it comes out. Okay, wherever it goes, here's where it is at time t, and here's where it is a very short time later. In what direction is it moving? Well, at this very instant, it's probably moving tangent to this curve, isn't it? But the tangent changes from here to here because it gets some curvature. Okay. Now we can prove that, and been able to get through this quickly. We can talk about that. Why this is tangent, but intuitively, you'll have to stick with intuitively from now until you see it in your text. When you do, pay close attention to it. Okay, but excuse me. Turns out the smaller your delta t gets, the closer this gets to the direction of your curve. And you get your tangent. Okay. So that your v is tangent to the curve, assuming your functions are all continuous and smooth. Continuous and continuously differential. Okay. In the homework you have for next time, you're not doing any of this. You're doing a lot of limits and domains and a couple of other things. Okay. Now I'm skipping to what you do when you use a limit, so you understand why you're doing the dang limits. Okay. Make sense? You're doing the limits so you can understand that the velocity at this point is obtained by a limiting process and gives you a tangent, right? A tangent direction. You divide the velocity by its magnitude, you get a unit tangent vector. Okay. You then calculate another derivative, which is the acceleration, which is the rate at which this velocity is changing. The velocity goes this way here to slightly this way here, you get two vectors that are offset like this. So there's a vector in this direction. That's your acceleration. If you're speeding up, that vector twists this way. It's not quite perpendicular to the curve. Maybe it's not even close to perpendicular to the curve. The acceleration you get is a centripetal acceleration, which is why you feel like you're being swung out when a car goes fast around a curve. Just imagine driving your car in this three-dimensional. Okay, you got an airplane. Okay, I'll give you an airplane. You can go out and practice. Practice doing this curve. Okay, what are you going to feel right here? Yeah, especially if you just step on the gas right here and you really accelerate. You have an acceleration in that direction, which tends to, maybe make you pass out and stuff if you're on a fast enough plane, and an acceleration in this direction. Okay, pushing you back in the seat. How are you going to understand that? How are you going to learn to fly that fancy plane I'm going to let you work with? You don't understand these limits. How are you going to know what's happening in the instant if you can't do the calculations? Well, in fact, nobody does those calculations in the instant. You do them elsewhere, so you get an intuition about it. Now, you're probably not going to be flying my fancy jet because I don't have one. But you're going to be engineering things where these kind of changes become important. Okay, maybe you have a path through a material where there are material changes and there's a temperature divergence and all kinds of stuff, and you got to make sure the material doesn't crack. All right. That just came off the top of my head. I don't even know if it made sense, but there it is for posterity. Okay. If you got an electromagnetic field, how's the thing changing? At what rate does it change if you move this way or that way? You got any vector field. How does it change as you move in this direction, that direction, or the other direction? Coming up in the next chapter. Okay. Right now we've got to understand what it means to move on a path and understand velocity, acceleration, and even better, your acceleration, get your velocity, say, in this direction. Your acceleration is in that direction. That acceleration has a component in the direction of velocity, which speeds you up or maybe slows you down, but just this way. Okay. And perpendicular to this direction, which is what makes you understand that you're curved. Okay. It's, the feeling you're curved is just the fact that whatever you're riding in has to exert a force on you in that direction so that your velocity changes from this way to this way. It's Newton's second law. Force is mass times acceleration. You have a centripetal force, centripetal acceleration, all that stuff. You should have the tools to totally understand that for functions, vector functions in three dimensions. You can analyze them, assuming they're continuous, which any motion has to be, and smooth, which motion is ultimately, although if you run into a tree, it doesn't feel all that smooth. Okay. Feels more like an instantaneous change in velocity, and it's not why it's treated that way. Although it's instantaneous, there being infinite force and unit situations instead of just being splattered. Okay, so don't run into trees, especially if you're airplane. Again, the idea is you have a velocity and you have an acceleration. They're easy to calculate. Just take another derivative. Take the derivative of your velocity function. That means you just take your derivatives, your x, y, and z functions, and there's your velocity. Okay. Then project this vector onto this one. That's part of the acceleration that's speeding you up. And subtract that projection from this vector, and you get this. I'm not sure I said that right, but it's just this. Okay, same thing I talked about there. And that's your acceleration in the perpendicular direction. So now you have a tangent vector, and you divide it by its magnitude, you have a unit tangent. You have a vector perpendicular to that because you just subtracted the projection from the vector. Okay. And that tells you in what direction you're being pushed. And these two directions are perpendicular. And now you can take their cross product and their unit vectors, you get a unit binormal vector And now you got a three-dimensional coordinate system as you're driving my jet around in space. Okay? And that's really cool. And we get that by next week. Not only that, but you're temporarily at any point moving on a circle. Okay, your curvature keeps changing, so the size of the circle keeps changing. But in any instant, there's a circle where your acceleration and everything matches the circle. So we want to find your centripetal acceleration. Well, there's a simple formula for that, but it comes back to analyzing vectors. Okay, it's just v squared over r. Take how fast you're going here, the magnitude of your velocity, square it and divide by the radius, and you get your acceleration. So you get the radius if you know the acceleration of the velocity. That's called the osculating circle, and it has a formula. And when you can do an osculating circle, it feels really good. Not everybody gets there. If I put it on a test, it might even be a little bit of extra credit because you tend to really have trouble with it. You got to understand every bit of what we're talking about today before you really have a clear picture of all that stuff I was just talking about. Okay, so go back to this part of the video. After we've done the chapter, you judge whether I know what I'm talking about or not, or to what extent I know what I'm talking about. Okay, learn it better than I know it because you have a younger brain, more flexible. Of course, I've been doing this for 60 years. So. No, it hasn't been 60 years. It's been over 55 since I had the course. But I've taught it at least once a year, so usually 3 times a year for a long time. But still, you know, your flexibility ought to be a match for what I know after doing this for 100 years. Whatever, it's exactly. Okay, so do good in this chapter. It's really pretty neat.